Alright, here we're going to try and check our time base. What I've done is I'm using a triangle waveform. There's a reason for that. I could have used a sine wave, but the triangle wave, it's something that is easy for us as human beings to know whether it's correct or not. It's a straight line, a series of straight lines. So if you see that the line is straight, and you know that this scope was able to measure voltages properly from 0 to maximum and so on, which we did earlier in the vertical test, then and we see that we are getting a full cycle within the certain time band and so on, so that our time base is correct, then we also know that our linearity must be correct. Otherwise we'd have a distorted triangle. We don't. We have a linear triangle. So I'm going to use the triangle wave, and we're going to test our time base. Right now I'm feeding in a 10 hertz signal. Between 10 and 11, varies slightly. We'll say 11 hertz, but on the scope, on 10 milliseconds per division, and 10 divisions, that's 100 milliseconds, that would be 10 hertz. And we are filling up the full entire amount. Okay, if I kick up my, my scope now to 100 hertz, which you can see we're 99 to 100 hertz here, then I should see that I have one full cycle per division. So I'm down, come back up for the positive peak, and then on the division line I have one cycle. If I go to 5 milliseconds per division, I should be able to get 5 full cycles on the screen. There's 1, 2, 3, 4, and then 2 halves make 5. On 2 milliseconds per division, I can get 2 on the screen, and at 1 millisecond per division, going at 100 hertz, it's going to take 10 full divisions, but I can get a full cycle. Let's adjust that. Yeah, we're getting a little bit of noise, but at any rate, we're getting one full cycle in that 10 divisions. Okay, so if I go now and kick this up another decade, I'm at 1,000 hertz now, and I see that I have a full cycle every division, and I do. Then I can go to 0.5 milliseconds per division, I should get 5 cycles. 0.2 milliseconds, I get 2 cycles. 0.1, I get one cycle. Okay, that's one cycle for the 1,000 hertz in 10 divisions. Makes sense. Alright, so now let's go up another decade. I am now reading 10 kilohertz. I'm at 0.1 milliseconds per division. I've got a cycle every division. If I go to 50 microseconds, I get the 5 peaks. If I go to 20 microseconds per division, I get the 2 peaks. 10 microseconds per division, in 10 divisions, I get 1 full cycle. That would be for 10 kilohertz. If I kick myself up another decade, and we are now reading 100 kilohertz, I see that I have a full cycle in every division, up, down, 1 division. And that's at 10 microseconds per division. Times 10 would be 100 microseconds, so we're at 100 kilohertz, should be right. If I go to 5 microseconds per division, I get the 5 peaks again. 2, I get 2 peaks again. 1, I get 1 full cycle in 10 divisions. So we are at 1 microsecond, but it takes 10 microseconds per division. That's 100 kilohertz. Now I kick myself up another decade. I am now running at a megacycle. Trying to tune it in just to, yeah, that's pretty good right there. It's a megacycle. I see that I have 1 cycle per division. If I go to 0.5, I've got the 5 peaks again. 0.2, I get 2 peaks. and then I wind up in XY land because I have no more range. So I've gone through the entire sweep range from 10 milliseconds per division all the way up to 0.2 microseconds per division. And we've tracked right on the nose. Okay. So at this point, let's just discuss what happened here. First, we measured our calibration test point. We saw that we had 0.5 volts peak to peak, and that it corresponded to the scale on the screen. And we used that then to test vertical from 1 volt per division up to all the way down to 10 millivolts per division, and we tracked it very well. We did that for both channels. Both channels tracked and measured voltage as well. Then we went and using our triangle waves, we tested all of the ranges from 10 milliseconds per division to 0.2 microseconds per division. And that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 of the ranges. And we saw that our time base was accurate in 15 ranges. We also should be able to have observed during that entire period that we had a triangle wave being demonstrated. So we have linearity and we are faithfully reproducing our signal. And so we're reproducing our voltages properly, we're reproducing our signal linearity property, and we are doing it within the proper time base. So this is a good scope. The only thing left for me to do here now would be to try and measure our bandwidth, and we'll handle that in a minute. Okay, we want to test the bandwidth of this 30 megahertz scope, but I've got a few obstacles to overcome, and I wanted to describe them to you. I am right now, I have the trace on a 100 megahertz scope, which is going to be my reference scope, coming from my 20 megahertz generator, my sweep generator. Now the sweep generator is very nice because it sweeps the entire spectrum of its range, and it does it, you know, so many hundred times a second. I can adjust that rate, and we can see the frequency response of the scope then, so long as the frequency response of the generator is linear. But like right now, I can adjust this, and we can see that the generator is very linear on this scope, and this is in the range of 0 to 2 megacycles. Now if I was to bump the range up, we are now going up to 10 megacycles, and we see that we have a little fall off on each end, not much, fraction of a division relative to the center, but still basically linear 0 to 10 megahertz. But now if I implement 0 to 20, I get some oddities here. So we are not faithfully providing a flat signal amplitude into the scope. So if I'm going to try and read my 30 megahertz scope bandwidth with this, I'd have to bear in mind that my generator is also not capable of producing faithfully that signal. So what am I going to do? Well, what I'm going to do, we know that we are flat 0 to 10 megacycles, so the generator helped us there. But I am going to put a 30 megacycle RF signal from this RF generator onto the scope, and I'm going to adjust it for 4 divisions on the 20 millivolt scale here. And then I'm going to move the probes to the B and K, and we will then measure the B and K's response to that adjusted 30 megahertz signal. All right, I've moved the probes back onto the B&K 30 megahertz scope. And I have myself set up on my generator so that I am generating 0 to 10 megahertz, just as I did on my reference scope. And we see that we fall off slightly, a fraction of a division on both ends, and we rise in the middle, just as the B&K 100 megahertz scope did as well. So we're producing the same waveform that we saw on the reference scope, and that's because both of them are linear and capable in this range. Now I'm going to kick myself up 0 to 20, and once again we see the aberrations, but it's even a little more exacerbated here on this scope to the right hand side, and that's because the scope doesn't have the capability of the 100 megahertz scope. But we do know that it was producing faithfully 0 to 10 megahertz, and I wanted you to see that. And then next we'll do the 30 megahertz measurement. Okay, we now have a 30 megahertz signal coming in on this 100 megahertz scope. We are on the 10 millivolt per division scale, and we are running full scale 8 divisions, so peak to peak we are running 80 millivolts. And what we want to do now is to, let me point out that I am on band E of this B&K E200D, and we are at the 30 megacycle range right now in band E. Just proving my point. What we're going to do now is we're going to move the test probe from the reference scope, and we're going to insert it on the B&K, 30 megahertz B&K. We are also on the 10 millivolt per division scale, and we are at our full scale right now, and I'm going to multiply by 5 here so that we can see the waveform better. But what we see is we are running down 1 division. We are plus and minus 3 divisions, or 6 divisions total, whereas the 100 megahertz scope was running 8 divisions. So we've lost 1 division. But this is, again, this is 30 megahertz that we're reading, and this is the limit of the scope. And the magic number for anything that's plus and minus 4 divisions would be plus and minus 2.8 divisions, which would be the 3 dB down point. And we haven't hit that. We're close. We're at 3, but we still could come down another 0.2 of a division. So the point is, we are slightly better than the spec of that the scope bears. So we have not hit the 3 dB down at 30 megahertz. We are just slightly better. That's on channel A. And if I move to channel B, we should be able to see the same results. We'll do that. Let's adjust the position of B. Got it zeroed out, and we need to be on 10 millivolts per division. Okay. Once again, zeroed. And what I see is we are just slightly better than channel A. We are coming in about 3.2 divisions up and down. So we actually have just slightly better frequency response on channel 2 than we did channel 1, but both of them beat the 30 megacycles bandwidth that is rated at. So the scope is checked out. We've checked out vertical linearity. We've checked out vertical response. It was accurate. We were able to measure voltages and represent it properly on the gradical. We measured the time base, and it was accurate over maybe 80% of all the ranges that we have available to us. And we saw, because we were using triangle waves, we saw that the linearity was appropriate. And we now have checked the we have checked the bandwidth and found that the bandwidth was within spec. So folks, it's a beautiful scope. It's working very well. I'm proud to offer it to you. We will include a service manual and a new set of probes with it. So happy bidding, and talk to you later.